In today's lesson, we're going to be introducing the concepts of independence. So in the last lesson, we were looking at conditional probabilities, and we saw that sometimes knowing something about one event tells us something about another event, right? And so how can we know when that's going to happen, right? How can we know if knowing about one thing impacts our knowledge about another? And we capture these ideas through the idea of statistical independence. So in today's lecture, we want to understand what the concept is of independence, what it is, both intuitively as well as in a mathematically rigorous way. And from independence, we can also think about defining dependence. We want to understand the concepts of mutual independence, and we also want to understand some of the basic properties for working with independence or dependence. Right? And so to begin, I want to bring in the example of sports watching. I don't know who in this class necessarily watches sports. Maybe you care about something that is similar. I personally watch a lot of hockey, and I know that as a hockey fan, I'm going to follow my own rituals for when I'm watching the game so that the team that I cheer for can do as best as they can, right? So I'm going to have particular ways of watching the game. I'll cheer. I will be angry at people for jinxing the results, all of these types of things. Now, of course, what I do when I sit on the couch to watch the hockey game is not going to impact what's happening on the ice rink, right? Like I know that inside of myself. And yet I still sort of want to do it. And it's because I feel like there's this way in which, if I follow all of the right sequences of steps, I'm going to increase the probability that something good happens. But in reality, these are two totally distinct events. I don't have to wear a particular jersey. I don't have to eat a particular snack. None of this is actually going to influence the probability that the team that I'm cheering for is going to do well or not. And this idea is the idea of independence, right? What I do is independent of what happens with the team. And so because of that, these two things are totally unrelated to each other. And so how can we capture this notion sort of with the tools of probability, with the tools of mathematics? When we were looking at conditional probabilities, we saw that sometimes knowing about an event B impacts the knowledge that we have about an event A. If this does not happen, then we say that A and B are independent of one another. So one way that we can actually specifically write this down is to say that if probability of A and B equals probability of A times the probability of B, then A and B are said to be independent. Now, if they're not independent, we say that they are dependent, right? So independent, dependent, just sort of opposites of one another, though typically we're going to think about independence as the trait and then dependence as the absence of the trait. And we're also going to use this little perpendicular sign here. So if A and B are independent of one another, we write A and then the perpendicular sign B, and we read that out as A is independent of B. If they're not, then you write the same sign, except you draw a line crossing it out, and you say A and B are dependent, or A and B are not independent. Now, if we have probability of A and B, or if A and B are independent, then we have the probability of A given B equals the probability of A. In other words, knowing about probability of B, or knowing that B happens, does not influence our thoughts about A. And we can sort of see this from the joint probability up above, right? So the probability of A and B, we saw through the multiplication rule, is probability of A given B times by probability of B. And so in order for the definition to hold that the probability of A intersect B is A times B, then we would need the probability of A given B to equal the probability of A. Now, intuitively, independence means that the knowledge about A tells us nothing about B and vice versa, right? What I've done to cheer for my hockey team does not influence the results of the hockey game, right? And sort of vice versa. If A and B are independent, then we also know that B has to be independent of A, right? So you can swap the order of these things mathematically. The complement of A has to be independent of B. A has to be independent of the complement of B. And the complements of A and B are also independent, right? So you basically get independence not only of the events that you're interested in, but also of all of the opposite events as well. And this makes some sense, right? Because if I tell you A happened, I'm also telling you A complement did not happen, right? And so if knowing that A complement did not happen gave you information about B, well then knowing that A happened would have to give you information about B, right? And so you can sort of get this directly, or you could work this out through the properties that we looked at with our basic axioms of probability and those derived properties after the fact. If we have many events, so we're not just dealing with A and B, but we have K different events, then we can define the concept of mutual independence as well. With mutual independence, we can sort of write this down in a somewhat confusing way. So we say that they're mutually independent if for every subset of the events of every size between 2 and k, we have the intersection of them equals the product, right? So to sort of simplify this, in order for events to be mutually independent, you have to be able to take any subset of 2, 3, 4, all the way up to k events, and separate the joint probability of all of them, so A intersect B intersects D intersect and so on, equals that product, right? So it's not enough for it to just be in pairs of them. It's not just enough for it to be in triples of them. You have to be able to take every single subset of all of the events and see that that property still holds. It's easiest, I think, in some way, to just think about that as being the multiplicative property that we just saw on the previous slide has to hold in every single subset. I think it's a little bit more confusing to think about this written down in a way that captures that. But the idea is just that if you can generalize this property up to all of the ways that you could take subsets of these events, then we say that they're mutually independent. Now, if A and B are independent of one another, and B and C are independent of one another, it's not necessarily going to be the case that A and C are independent of one another, right? And this is important, right? You don't sort of get this transitive property of it. A and C could be directly dependent on one another, and then they could both still be independent of B, right? We get a similar situation happening if we're taking multiple events. So if A and B, B and C, and A and C are all independent, then it's not necessarily the case that they're mutually independent, right? And so thinking about that definition, the issue here is that we would need the properties to hold for A, B, and C as well, all as one, right? So you take the subsets of 2. Subsets of 2 does not necessarily mean that the subset of size 3 is going to be enough, right? And so mutual independence is the way of generalizing this past just 2 different events. Most of the time we're going to be thinking about 2 different events, but this concept of mutual independence becomes important for us later on. Now, when we're bringing up the concept of mutual independence, it's very important to distinguish this from the concept of mutually exclusive events. So if we have 2 events that cannot happen at the same time, we say that they are mutually exclusive, right? If A intersect B is the empty set, then we've said that those are disjoint. You can also say that they're mutually exclusive events. You can't roll a number less than 3 and a number greater than 3 at the same time, okay? Mutually exclusive events are always dependent. And I think that bears repeating. Every time that you have 2 events and you know they're mutually exclusive, those events are going to be dependent without fail, right? And why is that the case? That might seem sort of counterintuitive at first, but this becomes kind of obvious if you start thinking about it, right? Let's say that we take those 2 events, less than 3 on a roll of the die, more than 3 on a roll of the die, right? Now, if I tell you that the number that I rolled is less than 3 on a die, and I want you to tell me what's the probability that it's more than 3, given that it's less than 3, well, that probability is going to be 0, right? You know that that didn't happen. It can't happen because the event that I told you tells you that it can't happen, right? And so because of that, we're always going to have this dependent structure. So it's really important to remember that mutually exclusive events are going to have a very strong dependence in them. Mutually independent events cannot be mutually exclusive. Okay. So that's basically the study of independence broadly, right? So independence is going to give us this idea that some events don't give us any information about other events. We can be thinking about defining this either through the joint probability, probability of A and B equals probability of A times probability of B, or we can think about this through conditional probabilities. Probability of A given B just equals probability of A. Now, if we have independence between A and B, we also have independence between many of these derived property or the derived events from there, right? So the complements in particular, sort of any combination of A, B, A complement, B complement are going to be independent of one another. Mutual independence is stronger than sort of pairwise independence when we have many different events. And mutually exclusive events are not independent ever. Okay. That sort of gives us this framework for working with independent events. And independent events are going to come up over and over again when we're studying questions of probability because they're sort of the easiest events for us to work with. And in the real world, very often we're going to be able to say that two events, even if they're not exactly independent, will behave close enough to being independent for us to do some calculations that are greatly simplified. So we'll start looking at those types of calculations in the next lesson, and I hope to see you all there.